and then start. So what we will learn today is we will learn some new material, and it's about recursion. Okay. So we will learn recursive method. And the example is on our course website, it's Java recursive example, okay. So far, if you recall for our method, so Java method. So in a Java method, it can call other methods. Like a main is a Java method, it can call some other Java methods. Is it? Or you define a Java method and it can call other Java methods. Okay, so there is no surprise for that. But we haven't seen a method call itself. Call itself. So what is that? Is that allowed? Yes, it is allowed. So if a method call itself, then it's a recursive method. Okay, so that's called a recursion. You call yourself. Okay, so how can a method call self? Is it? So let's just kind of see. Is it? So you have a method like a void function. Then within it, you call yourself. Suppose if you just write a method like this, then you call yourself, it's just keep going forever. It's never going to be terminated. So that's going to cause a problem. And if you recall in previous unit, when we learned stack, and we also know for function call, it involves in operating system called runtime stack. So runtime stack, that means each time you call, so generally speaking, we always, any application, you always have main. The main is the entry point. And within, so here you have the main call function. Is it? Okay, and then by this, you call yourself, so then it call itself again. And then it call itself again. So it can keep going. Is it forever, kind of? But your runtime stack, it has capacity. So it won't allow you to keep calling forever. So that will cause a problem. Okay. So even though this concept, a function call itself, the concept, this is called recursive method or recursive function, call yourself. But here's a problem that as we just analyzed. So if you wanted to define a recursive function, then you also need to provide a stopping case. So your function must, so if some condition, then it should be stopped. Okay, otherwise, it can keep calling yourself, calling the function self. Okay, and calling the function self, basically, that's more related with you recursive. So this we can call it as a recursive case. Recursive case. Okay, so generally speaking, for a recursive method, is made up of two parts. Okay, a stopping case, or sometimes we call it a base case or anchor case, and the other case is a recursive case. Okay, for the stopping case, normally it's some condition, is it? So certain condition meets, then it's not going to call the function itself, it will stop. Okay, and all the other case, then to keep calling itself. But keep calling itself, if you just call itself, it won't change. Then it's kind of impossible to bring your method to the stopping case, is it? So with the recursive, you call yourself, so the recursive call to self also needs some scenario for reduced. Okay, for reduced cases. Okay, only in that case, you reduce, then you can bring your case gradually to the stopping case. If you never reduce, it will never reach the stopping case. Okay, so whenever we write a recursive method, you must need to provide these two cases, and you also need to you also need to provide the reduced scenario, okay, so that it can bring your recursive call to the stopping case. Okay, so that's general the idea, okay. And then, so a lot of time for the recursive function or method, so we just implement in recursive way. Okay, in recursive way. And after all, later on, we will see from the example, basically recursive way, a lot of times kind of involved loop. That kind of involves some loop because you just go back, but with some reduced case scenario. They involve the loop. But with the loop previously, what we learned is called iterative. Okay, so generally speaking, the loop we have learned is iterative way. So a lot of scenario you can implement in iterative way. You can also implement in recursive way. Okay, when you have choice to do iterative way, this is more efficient. And why we see this is more efficient? Because with loop, there is no function call overhead involved. Because otherwise, with recursive, is it you keep calling yourself, but each time you need to push the method to the step, and then you also need to pop when you finish. Then you need to push, and then you need to pop. Then you need to push, and then you need to pop. So that has the function call overhead. But if you implement in iterative way, there is no function call overhead. So that's why we say it's more efficient. So generally speaking, after we learn recursive method, don't get all of your loop, then just say, oh, I do recursive call. No, that's not recommended. Okay, it's just some scenario, some approach that some task you cannot solve it with with iterative way. Then we need to borrow recursive concept. Then it helps us to solve the problem. Okay, and generally speaking, if iterative way can be used to solve the problem, then it's more efficient. Then just go ahead with iterative way. Okay. So that's the general idea about recursive. And after we learn recursive, then we know, so recursive also versus iterative. So keep this in mind also, okay. And then next, let's take a look, okay, some scenario. So the first one we will see is do the factorial calculation. Okay, in math, it's pretty straightforward. As a factorial is just we write like this in exclamation. So basically, it's equals 1 times 2 times 3 times all the way to n. Is it? And if we write it, okay, we can also say, okay, 1. So if n is 1, then it is 1. Is it? Otherwise, we can write it as what for factorial? We can write as n minus 1 factorial times n. Is it? So the previous numbers factorial times n. Is it? And if we write it in math formula, then it's going to be Fn equals Fn minus 1 times n. Is it? In math, we can write something like this. Basically, we can also translate this into a Java method. Is it? So let's see how we are going to do that. So that's regarding factorial calculation. Okay. For this factorial calculation, so the return time is some big integer long, okay, and the parameter is an integer, okay, for this factorial. So let's see, okay, we call this is a base case. So in math, when we see zeros factorial, we see it's 1, okay, and the 1's factorial is also 1, is it? Okay, so we can see this is as a base case, or we say stopping case. And sometimes we also call it an anchor case. So this will let it stop. Okay, then you say, okay, I'm just return 1. Otherwise, I'm going to use this number n times the previous one. Is it? So this is the recursive case. You call yourself, is it? Call self, but with reduced parameter value. Is it? Well, basically, it's reduced argument here. Is it the value reduced, not n? Okay. Then just think about, then for the next one, it's going to be n times n minus 1 times factorial n minus 2, is it? So it's reduced. And to a certain point, to keep reducing, it will reach this n is 0. Is it? When n is 0, okay, I find it. It's 1. But you may see, you just get 1. How can you get to n of that? Then it's going to be proper back. Is it 2? Okay, 1, then times 1, and then times 2, and then keep doing. Is it? So that's how it works. So we can keep tracing, then see how the recursive function calls. Is it? We can call like a factorial 5. Is it? So let's see. So I just write with abbreviation version. Okay, suppose we just write as F5. Is it? Okay, so the argument you plug in is 5. Then what it's going to do? It's going to call 5 times F4. Is it? With F4, then it's not a stopping case. So it's going to call this. So n is 4. So then it changes to 4 times F3. Okay, and with F3, so now the number you plug in is 3. So n is 3, so it's changed to 3 times F2. And then you plug in 2. So with 2, then it's 2 times F1. Okay, then you plug in 1. With 1, then it's 1 times F0. Is it? Okay, and then with F0, we know it returns 1. So this, it gives you 1. Is it? Once it knows the 1, then you resume back to the previous one, because in the stack, so here is main, and then you have F5, then you have F4, then you have F3, F2, F1. Is it? Then you have F0. Okay, F0 is the top one. It returns 1. So you have that 1 return. So now F1 is the top. Okay, F1 is the top. It's what? It returns 1 times F0. 1 times F0 is what? Is 1. Is it? So you have that 1 calculated, then it's going to bring it back. Is it? Okay, so this one popped. So now it should come back to this statement again. So then it's 2 times F1. And you have F1 is 1. So it's what? It's 1 times 2. So you have 2. Then 2 is going to be proper back. So you remove this from step. So now F3 is the top. F3 is the top, so it's 3 times what? F2. Is it? F2 is what? Is 2. So 2 times 3 is 6. So you finish. Is it? Finish this. Okay. And then you have F4 is at top. When you have F4, it's come to this statement. resume back to this statement. And this statement is the what? Is 4 times F3. F3 we already know is 6. So 4 times 6, so it's 24. Okay, so now you finish this, you go back. Is it? So it's F5. 5 is what? Is 5 times 24. So 5 times 24 is 120. Okay, so 120, you also got it. So now you know F5 is 120 and you return. Is it? So for the recursive function, we can clearly see from what we just traced. Is it? Whenever you call the reduced case, that function has got to push to the stack, push to the stack. Is it? When it gets to the stopping case, it finishes execution, then it's proper back, and then all the way to your first call. Is it? To the first call, and then you find the result that you need. Is it? So this is the concept of writing a recursive function and how it's executed, okay? And we can also see if there are too many call to itself, then the runtime stack is going to be involved very deep. Is it? We can also clearly see if you don't have the stopping case, suppose over here, we don't have that n is 0, 0 stopping case. It's going to keep calling, is it? Then it will bring the stack broken, is it? So this is the concept about a recursive function, okay, recursive method. So you must have base case, and for your recursive call, you must have the reduced case. Okay, you must reduce your call, okay, plug in. Initially it's n, is it? Then you need to bring it to n minus 1, so it can keep reducing, make it to reach to the base case, okay? So whenever you write a recursive function, method always keep in mind to check if you have the base case and if you have the reduced recursive call, okay? Unless you have both, then that means your recursive function is right on track. Otherwise, it's not, okay? Keep this in mind. And also, for the next example, we can also see the base case is not just a single one. You can have multiple base case, okay? Okay, so that's the first example, okay? The first recursive function. And over here, we call it, that we can run it and see our result. So the first one is just give us the result. It's 120, okay? And then let's take a look at the second one. The second one is about Fibonacci number. Okay, Fibonacci number is 1, 1, and then 2. So you add the previous 2, okay? And so the next one, you add the previous 2. Then it should be 3. And for the next one, you add the previous 2, so it should be 5. And then the next one, you add the previous 2, so it should be 5. The next one, you add the previous 2, so it should be 13. And the next one, you add the previous 2, so it should be 21. So it's kind of keep going, okay? So this is the first Fibonacci number, the second Fibonacci number, the third, the fourth, fifth, sixth, seventh, and the eighth. Okay, so it's keep going, like this. You add the previous one, okay? So this is called the Fibonacci number. So let's see, how do we write a Fibonacci number? Okay, and of course, for like a factorial, if we use a for loop, that's achievable. That it can be implemented with regular iterative implementation. And it's more efficient, but here we just try to use the recursive to explain how to write a recursive method, okay? For factorial calculation, the recommended is not to do the recursive, is do iterative implementation, okay? Same thing for Fibonacci number calculation, but here we just try to use it to explain the concept about recursive method. So next, let's see the Fibonacci number calculation. So this is a Fibonacci index, okay? So when it is 0, is it the first number, then it returns 0. When it is second one, Fibonacci, it's 1, then it is 1. Okay, so if we start at 0, it's the same, is it? But anyway, both of these two cases are base case. Okay, base case. Then starting from the next one, it's you add the previous 2. So previous 2 is index -1 and index -2, etc. So this involves you reduced by 1 and then you reduce by 2. Okay, so this is a reduction. Okay, here we have base case. Okay, 2 base case. So in this this implementation of the Fibonacci number, so it includes both base case and the reduction case. So it will work, is it? And we can also do tracing, is it? So tracing here is a Fibonacci 8, is it? Okay, for this Fibonacci 8, so then baseline, it's not 0, it's not 1, so it should be reduced as Fibonacci 7 plus Fibonacci 6. But with Fibonacci 7, then it should further reduced as Fibonacci 6 plus Fibonacci 5, is it? And here it's reduced as Fibonacci 5 plus Fibonacci 4. And we can keep doing. Is it Fibonacci 6? That's a repeat of the previous, is it? But with Fibonacci 5, then it's easy to figure out Fibonacci 4 plus Fibonacci 3, is it? And with Fibonacci 4, then it's keep reducing as Fibonacci 3 plus Fibonacci 2, is it? And with Fibonacci 3, it's Fibonacci 2 plus Fibonacci 1. And with Fibonacci 2, then it's Fibonacci 1 plus Fibonacci 0, is it? So this is kind of looks like a tree, is it? So kind of like a recursive call tree, is it? Okay, then we see whenever it reaches this, so and all of this can keep going. Okay, so we are not going to go all of the detail. Okay, so we just try to go with the way to reach the base case. So both of this are the stopping case. So this one we have 1, and this one we have 0. So Fibonacci 2, then it's 1 plus 0, so it's 1. We get 1. And the Fibonacci 1 is also 1. So Fibonacci 3 is 1 plus 1, so plug it back, it's 2. Is it? And Fibonacci 2, we already find it's 1. So then we figure out Fibonacci 4 is what? 1 plus 2, so it is 3. And we have Fibonacci 3, Fibonacci 4 is 3, and then for the 5 it's 4 plus 3. So 3 is 2. So then you plug it back, it's 5, is it? And then Fibonacci 6 is 5 plus 4. It's 5 plus 3, so it's 8, is it? And over here, okay, Fibonacci 6, we already find it's 8. And the Fibonacci 5, we also find it's 5. So that's how we find Fibonacci 7, so it's 13. And you have Fibonacci, you have Fibonacci 6. So we can move it back, then it's addition of this, then we come up with Fibonacci 20, the result is 21, is it? So with this tracing tree, is it, we can also trace it back, is it? But in programming, it has a runtime stack to keep track of the function values, is it? Then to keep track and always push it back to the original, okay? And then we can find the result, okay? So that's how we trace it. And then let's see the running result. Yes, it is also 21, okay? So that works. Okay, for the next one, what over here is for the 2 to the power, is it? So in math, 2 to the power calculate. And before we learn recursive, we know for sure this can be implemented using iterative way to implement it. It's a pretty straightforward. It's just a for loop, is it? And you keep accumulation, is it? And this is more efficient. Always keep this in mind, is it? Because no function call overhead. Okay, so this is more efficient. And but of course, you can also implement it using recursive way. Okay, recursive way is, so 2 to the 0, then it's 1. So the base case. And then here is the recursive call. And here is the reduced case. Is it? And you reduce by 1, is it? And so this is also pretty straightforward, okay, for 2 to the power, okay. And for 2 to the power, and here we do the 9, is it? So let's see. So 9, 2 to the power, no matter it's iterative or recursive, the running result is the same, is it? But if you consider like the time running, then the iterative way should be faster, okay, should be faster. Okay, the next one is about search. For this, we consider search an item in some kind of, we consider here linear collection. In some, we call it linear collection. Okay, linear collection. So then let's see. So over here, we have an array. And the array has all of those integers, is it? Then we try to find some item. So find some item in an array. Okay, in an array. So how are we going to do it? Is it? So basically the way so far we have learned is called linear search. Linear search is involved compare 1 by one in the array. In the array, is it? So this kind of search, we can call it exhaustive search, because you're going to find sometimes involved. You need to compare almost everyone in the array. Okay, so this kind of search, we call it linear search. So the way we already know that, so you just, okay, so suppose in this case, you want to find the 7. Then you start from the beginning, compare, compare, compare. Okay, here you find it. Then you are done. Is it? So it involves 3 comparisons. Okay, suppose if you want to find the 29, then you need to compare all the way to 29, all the way to the last. Is it? So then it involves 1, 2, 3, 4, 5, 6, 7, 8. Then it involves 8 comparisons. Okay, so all the way. And if you want to try to find, suppose here 0, you also need to compare every one of them. But it's not in the array, is it? So also involves 8 comparisons. Okay, but over here, our array is not large, it's quite small. Assuming you have some array size, go to millions. Then just think about, suppose the item is not there, then you need to do what? Compare 1,000,000 times. Then you say, okay, that item is not in the list. So that's quite of wasting of the time, is that? So in computing, this is not a very efficient way to do the search. Okay, to do the search. So there is an improved version search called binary search. Okay, for the binary search, but if you want to the search to function as binary search, there is a precondition for the search list. Is the list must be sorted already. Okay, must be sorted already. Otherwise, it's hard, okay, to do the binary search. So over here, for the binary search, the idea for it to work is because it's already sorted. That suppose we have like, suppose now 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, something, okay. And suppose we want to search some item, assuming we wanted to search 11. Then the idea is we split, we first find the media of the item, okay. The media items is 6. It's 6, then you compare, so basically the middle one, okay. The middle one in this case, then it's number 6, the middle one in the list. And then you compare the item with this one, okay. With the middle one. And if it is So 11 then is greater than 6. Is it? 11 is greater than 6. This is already sorted. This is already sorted. If it's already sorted, can 11 be on the left list? I suppose this is the right list. Can it be in the left list? Definitely not. Is it? So you can completely drop it because it cannot be in that list. Is it? So what the next part is, you just need to carry about the right sublist. Within the right sublist, then we can continue doing this. Is it? So you find the middle item, that is 9. Then you compare 9, or compare the item you want to search with 9. And if it is greater than this item, that means this left list shouldn't be considered anymore. It can only be in the right half. Is it in the right half? Okay, so we drop the left. And then for the right part, then you find the middle item. The middle item is 11, then you compare with it. Oh, you find it. Is it? We find it. So totally, how many comparisons? That we just did. We first did with 6, then with 9, then with 11, just 3. Versus, suppose we do linear one. Linear search, you need to do how many comparisons? Starting from 1 all the way to 11, you need to have 11 comparisons. Does this save a lot? Yes. Does it save a lot? If it is goes to like millions, it's save more. Okay, because for the binary search, then it's going to be log 2n. Okay, versus linear, it's n. Okay, linear is n if we draw the mass curve. Is it for the linear, it go like this. For log, then it's go to with this. Okay, to go with it. And then just think about when the number increase. So here is the n, number increase. So the rate we can see for log, it rates small, but for linear, it rates quite fast. Is it? So that's why we see the binary search compared with the linear search is faster. But there is a precondition, the list must already be sorted. Is it? And it won't be fast if your list is not sorted. If it's just a random one, then binary sort, it doesn't have any advantage. Okay, so it's only applied for the sorted one. So then next, let's take a look how we implement the binary search. Okay, and this is a recursive implementation. So you have the array as a parameter. So here is the item you want to look for. We call it a key. And here is the range. So search range index. Okay, search range index, low and high. Okay. And then let's see. Okay. So you need to find the middle item where it is, the index. Okay, and then you compare with the key with that item. If it is less than, is it? Then we just, so here is that middle item. So here is the left part and the right part, is it? And this is less than the middle. If it is less than middle, you just need to worry the left part. The left part should be from what? So here is the index of low. And here is the last item of the left should be the middle's index -1, is it? So the low part index not change, but this part index change. So basically this is reduced. Is it? This is reduced for the high part, it's reduced. And if it's the right part, then the low index updated to mid +1. Is it? So this is mid +1. So it's also reduced. It's reduced for the low part. Is it? So in this case, you have two recursive calls. So that's also fine for recursive method. Okay, you can also have more than one recursive call. Okay, but both of them need to have reduced case. Both of them reduced. Okay, and otherwise, if it is that item, then you just return it. Is it? So this is the base case, but there is another base case, is it? So if like the item is not in the list, so that means your search list exhausted without find a match. That's what a scenario is your low index, is it? Because you're going to keep updating, is it? So then your low index go too high. So it depends, because over here, it can also be updated, is it? So if this is keep updating, then that's going to go beyond. So the low still greater than high. As if this is going, then it can go over, is it? So then that means, so if your low index is already greater than the high index, then you also need to stop. So this is also the stopping case. So there are multiple stopping case and multiple reduced case. Okay, that's what this example shows. Okay, and then in this case, we just return some negative index. And we can take a look what we did here. We call, okay, for this array, then we try to find 7, try to find 0, is it? And we did find it, is it? For that 0, it doesn't exist, so it will return a -1 index. Okay, so that's the idea about